Alright, so this is Professor Gilmet, and I'm here today to talk to you about descriptive statistics. And this is something you probably already know something about from your high school days, but the objectives for this lesson are basically, we want you to be able to calculate and understand the mean, to be able to calculate and understand the standard deviation, to be able to calculate the median, understand what it means, and to calculate the range, pretty easy, and then to calculate quartiles, which are actually sometimes hinges, okay? And so, why is this really important? Again, the brain just doesn't do well with large data sets, right? So we need a way to summarize the data. However, some data is better represented by the mean and standard deviation, while some is better summarized by the median and quartiles, right? And so using the correct measure helps you to correctly understand the data and not be misled, right? So this is a common theme in our statistics section, is not being misled. And so here, what is the mean? So the mean the best measures try to take into account all of the values of the data. And so the mean and standard deviation use the values of all the data to obtain a measure of center and variation. Okay, that would be the standard deviation. So the mean is the arithmetic average, hence the shortened average, which means mean, all right, of all the values, and gives you a value where the data balances. Okay, and so we've got a super short formula. X bar, right? X bar is the sample mean, and what that means is that you take the sum of all the individual values, x sub I is individual values, and divide it by the total number of values. And so the sum of all the values divided by the number of values. Okay? And this actually gives a balancing point for the data. This is something I discovered when researching for it, not discovered, but maybe thought about in a different way when I was researching this lesson. And think of the data sitting along a long plank, right? Think of the axis, right, that's being stretched out, and you're going to put all of the data on it. And so the mean is the support point that allows the plank to balance, right? So if you see this picture over here, right, then that data on each end, right, is balancing on this point right here, on this. And so, in fact, we can actually prove that they balance, right? So a nice example, Clark Howard is a financial advisor, and on his website, he looks at the top 50 paying college degrees during the first 5 years after graduation. And I actually provided a link so that you can look at it. Now, we can certainly calculate the mean of 50 numbers, but that would take time, right? So here's the actual data right here. And so you see each of the degrees, mathematics, 54,000, right? Architecture, 50,000. English, 45,000. Journalism, 45,000. So this is the median salary after 5 years, right? Graduated from college. So I've got those there. Now, what we could do though is we could calculate the mean in Excel. And because the mean is the arithmetic average, we actually use average data. Okay? And so we're going to use the average function. So let's go ahead and back to our data here, and that's exactly what I'm going to do. I'm going to go over here a couple of spots, and I'm going to say, hey, look, equals, right? Average starts to come up, so I hit tab. And now I want this data in here, and it goes all the way down to B51. And so I'm going to hit enter, and I see that it's $49,354, right? And so there it is, 529. Ooh, let's see, 5. Let's see. Did I go all the way down? 554 B51. Yep. Oh, okay. So I got a misprint here. 49,354. 49,354. But why is it the balance point, right? What would happen if we subtracted the mean from all of the data, right? The high values would be positive, and the low values would be negative, right? In other words, you'd have the high values on one side above the mean, and you'd have the low values on the other side below the mean, right? And in theory, they're stretched out across this plane, but you can think of positive values and negative values, right? So what does that look like? All right, so let's go ahead and do that. Now, in stats, we call this the deviation, right? The deviation from something. And I don't actually like how that looks, but there we go. So there's the deviation. And so that's going to be equal to this guy minus 49,354, right? And what I want to do is I want to make sure that this is actually formatted as currency to 2 decimal places, okay? Now, I'm going to copy this, and I'm going to paste it all the way down. So it's going to subtract the mean from every value along here. And so you can see this is $20,000 above average. This is $10,000 above average. Here's $646 above average. And now you have below average are these right here. And so these are the negative values as we go down. And so biology pays about $8,000 below. Okay, so what do we have to know? So that's the deviation, right? And so we've got all of these values here. Okay, so what happens when we add them, right? So I've got some values that are positive, and I've got some values that are negative, and then we add them together, right? So let's go ahead and do that. Now we know that that function in Excel is to sum all of the values. And so we're going to sum all of the deviations, right? And what we see is, it's $6. All right, hold on, I got to fix something. I'm going to pause the video. Okay, sorry about that. It turns out that there was an extra 12 cents in the average that I needed to subtract from each of the deviations. And that was really important because when you sum them up, you actually get 0, right? And so that means that you have just as much positive value as you have negative value, right? And so the positive and the negative values balance each other at the mean, and you see that the sum is 0. And so there's just as much value above the mean as below, and it really is the center where the data balances. And this is actually pretty cool, all right? And this leads us into a discussion of the standard deviation. This is actually where the name comes from, is that deviation is subtracted from the mean. And so the standard deviation is the average of all the distances from the mean, right? That subtraction that we did. And it is a measure of variability in the data, right? If the standard deviation is small, then all the data is very close to the mean. But as the standard deviation gets larger, the data is moving on average away from the mean, right? And so you get more variability. Now, we've got this formula for the population, right? So when you have all of the values for the entire population, you use sigma, okay? And with sigma, you take those deviations and you square them, and then you add them all up. Wait, what's with this square rooting and squaring and stuff in the formula? Well, remember, the mean balances the data such that the deviation sum to 0. So how do we work around this problem? Well, we square everything, right? So I square all of those deviations to make it positive. Then we add it to something that sums to other than 0, right? So if you think about it, if you've got 1, 2, and 3, and you take their subtractions, you get -1, 0, and +1. If I add those up, I get 0, right? But if I square them, I have a +1, a 0, and another +1. Now they don't sum to 0. They sum to something else. And so then I can divide it by the number of values in my data set. But to undo the squaring that we did, we're going to take the square root at the other end. Otherwise, that number is too big, right? And so I take the square root of everything to get rid of that squaring that I did to make everything positive. And so this is for the population. Okay? But the formula for the sample standard deviation, when you only have a sample of values from the population, the values actually tend to be closer to the sample mean than the actual population mean, and they show more variability. So this is a little bit of a mess. And so Bessel, wow, he did some really cool stuff and showed very convincingly that the way to handle this was to make the denominator smaller by subtracting 1. And very specifically 1, not some other number. And so why are we making the denominator smaller? So that the result of the fraction gets a bit bigger. And therefore, we actually have S is the sample standard deviation. We're going to still do the same thing with our deviations. We're going to square them and sum them up. But instead of dividing by just n, we're going to divide by n minus 1 to make the fraction a little bit bigger so that the sampled standard deviation is just a little bit bigger. So I want to show you that here in Excel, right? Oh, a little more detail you can actually watch here. This is a Khan Academy video, and it gives a really nice intuitive explanation for why we use n minus 1. Now, calculating the standard deviation in Excel, you don't want to forget that there are 2. So when you start typing in Excel, make sure to select the correct one. For the population standard deviation for sigma, it's stand dev p for population and then your data. And so from here, if I want to do the standard deviation of here, I'm going to do equals stand dev, and p is the first one. I take the data and I get 8,111. Now, if I want to do the sample standard deviation, S, right, for sample standard deviation, then I use an S instead of a P. And so if I come over here, I go equals stand dev S. And so I can do this. And you see it's only $80 more, right, out of 8,000. So it's like a 1% difference. And so what a learning mathematician said is, if you're worried about n or n minus 1, then you're probably trying to do something sneaky with your data. Now, I don't necessarily agree with that, but I would say that going forward in your statistical career, if you can't remember which standard deviation to use, either one of these is going to be pretty close to the other, and that makes us pretty happy. Okay? So I wouldn't sweat it except for the homework. All right? Now, this brings us to the median. And so the median is the middle value of an ordered set of data. And I want to underline this ordered set of data, right? Because if it's not in order, you're not calculating the median. So if you have an odd amount of data, then the value that splits the data into two equal size sets is the median, right? And so, for example, right, if you actually just have 1, 2, 3, 4, 5, this is an odd set of data. This, let's pick a folly color, right? 3 is your median. And the reason 3 is your median is because this is the same size as this. Okay? So you've made it two equal parts. Now, if you have an even amount of data, then the two values on each side of the split get added and divided by 2 to find the median. So going back over here, I'm going to erase that fill, right? If I make this, right, this is an even number of values. Well, this 5 through 7 right here, right, this is one split, and the 1 through 4, that is a different split. So the median is in between the 4 and the 5, right? And so you take 4 plus 5 and add them together, and then you take that 9 and divide it by 2, and this is your median, okay? And so 4.5 is halfway between 4 and 5, and that bridges this split right here, okay? So therefore, with odd data sets, the median is a data value, while with even data sets, it is a calculated value, which I just showed you. And there's something nice about the median actually being a data value, all right, which is very rare with the mean. The median actually has a few nice properties. First, super easy to calculate. Just put everything in order and find the middle. Second, many times it's an actual data value, which statisticians really appreciate. And last, because it only uses position and not the values of the data, it's really resistant. It's really resistant to extreme values. Okay, and so I'd like an example to illustrate this resistance, right? Let's say we wanted to know what the average player on the Golden State Warriors makes for a season. Right? We could always use the mean. This takes into account all of the values of the salaries. Surely this is a good indicator, right? Surely. So let's go over, and I'm going to go to sheet number 2. Right? And I've got the player's name, Kevin Durant, Klay Thompson, Dre Green, and then I have their 2016-2017 player salaries. Now, there are 4 players at the bottom that are making less than the league minimum. These guys are on like 8-day contracts or 3-game contracts or something like that, and then they can be released. So because these guys are not making the league minimum, because they're not full-time salaried players, I'm going to take them off. All right, I'm not going to include them. So I'm just including the full-time rostered players, the 17 guys from Elliott Williams to Kevin Durant. All right, and so let's take a look at what happens when we take the average of those salaries right there. I get $6,287,000, right? Basically about $6.3 million. $6.3 million, right? So the mean ends up being $6.3 million, and only 6 out of 17 full-time players make more. Let's go back and look, right? So here is 6.8. So Jason Thompson, Andre, Steph Curry, right? Draymond, Klay, and Kevin Durant. These guys, they all are in the green, right? They're all making above the league average. But these guys down here, none of these guys are making that league average, right? And so you actually have most of the team making way less than $6.3 million. Okay? And so this doesn't actually seem to represent all the players because they're making less than $2 million very well. Let me read the sentence that I wrote instead of trying to ad-lib. This doesn't seem to represent all the players making less than $2 million very well, right? Look at all the, right? You've got, in fact, all of these guys are making less than $2 million. We could paint them red, right? Say, look at that. You've got 1, 2, 3, 4, 5, 6, 7, 8, 9 players. You actually have more players making less than $2 million than you have making above $6 million. That's crazy talk. Okay? So, in fact, with incomes, housing, or other types of data that really don't have a maximum, right? Like, home prices go way up. Think about some of the incomes that like Bill Gates or Warren Buffett or some of these guys make, right? Other types of data. I know children. I have 5 children. There are people who have more children than me. Duggars, right? So the mean can become really inflated by just a few values. For the Warriors, it's Kevin Durant, Thompson, and Green that move the mean to be so high because their salaries are so much higher than everybody else's. It really pulls that mean. And so what should we use? Well, when you have extreme values, then using the median is the best choice. And so here we see that the median is $1.5 million. Okay, and so let's calculate that. So here we go, equals median, and there it is, it pops right up, of my data set right here. And I get the 1.6, 1.5-ish million. Excuse me. And so if we think about that, and exactly half the players make less and half the players make more. Let's get rid of all of this fill right here that I've been doing. And this 1.5, this is this value right here. This Anderson actually makes the league average. And so you actually have 8 players that make above the league average, and you have exactly 8 players, full-time players, that make below the league average. And so this really is the central value for this particular group of guys. Right? This would be the representative value that you would say. Not the $6.3 million. That makes people feel good. Oh, the average is $6.3 million on the Warriors. But it really doesn't, it's really not representative. Okay? Just like if Bill Gates moved into your neighborhood and built a house, you wouldn't want to say that the average income of the neighborhood was $10 million now because he lived there, or that the average house was, $2 million because he lived there. No, you would want to use the median. And in fact, home prices are almost always given as medians because that is a way more representative value when you have a few extreme values. Now, with the mean, we had the standard deviation. For the median, we have the range, and the range is a very simple way to calculate variation in the data. And the formula is super straightforward. The range is the max minus the min, and you would actually calculate it in Excel doing max minus min, okay? Unfortunately, there's no range function, but the functions you use are the definition, so it's not really that bad. Not as bad as that mult mode thing. So let's go ahead and do that real quick. So if I wanted to see the range of values here, you would do equals max, right, of all of the data, right, and you want to close it up minus the min, right, of that same data set. And they should match, they should be overlapping. And then when you hit enter, that would be the range, right? It's going to be 26,290,000. And that's because he makes over 26 million and this person makes $250,000. And so when you subtract those two values, that's where it comes from. I could do the same thing for the salaries over here. Let me kind of get rid of all of this formatting here. And we could do equals the max of all of my median salaries. Right? Uh-oh. What is it? B to B 51. Yep. All right, and then minus the min of B2 to B51. And then I hit enter, and you see that it's 28,750. And of course, if you take 70,000 and you subtract 41,000 from it, you would get basically about $29,000, which is what you see here. So this would be the range of values. Okay. Now, the problem with the range is that it's also super sensitive to outliers. One extreme value makes the range change. And the standard deviation is also sensitive to outliers, right? And so if we look at the range here, 26 million, that's almost the maximum value, right? Because it's so much bigger than the minimum value. So the range here is really skewed, okay? And so what measure of spread should we use, right? Well, the answer to that is quartiles or hinges, okay? which I'm going to explain. So better is to use quartiles than the range. There are actually 4 accepted ways of calculating quartiles. One definition is actually called a hinge, but most books don't address this. And there's a really nice discussion of the definitions and the rules calculating them here. I will say that after you read this, what you'll notice is that only for very specific types of data under very specific circumstances does it actually matter which of the 4 accepted ways you use. You're going to get answers that are so close together for the most part, it doesn't make any difference, right? And so the easiest and most accepted rule is to take an ordered set of data and find the middle of the half below the median for the lower quartile and the median for the upper half for the upper quartile, okay? And so if I go here, and I don't want to do it for the range of 50, right? But here I've got this median value, right? I've got this median. And so what I can do is I can actually find the middle of these 8 values right here. 1, 2, 3, 4, 5, 6, 7, 8. And really, I would cut it into these 4 and then these 4, right? That would be there. And so what would happen is I would find the median of this upper half of the data. And so that would be equal to this value plus this value divided by 2. And that would be your upper quartile, or Q3, right? And so down here I would do the same thing. I would say, hey, look, I have these 4 values, and then I have these 4 values. And so that makes a difference, right? Between these. And so the median is in between these 2. And so that would be equal to, right, this value plus this value divided by 2. And this would be your lower quartile, or Q1, right? And so that's how you would calculate it, right? You're just doing that. Now, if you do not include the median, that's a true quartile. Okay, so I calculated true quartiles. If you do include the median, then it's actually a hinge. Okay, it's just a different word so that statisticians know whether you're including the median or you're not. It turns out that a hinge typically has more data values as quartiles, whereas with a quartile, the way you're dividing it up into 4s, you have more calculated values. And so for some statisticians, they want actual values there. Again, if you're worried about this stuff, you know, it doesn't make much of a difference for the most part. Okay? So for a quartile in Excel, you can actually do quartile excluding, that excludes the median, that's how you know it's a quartile, and then the data and the quartile you want, either the first quartile, the median, or the third quartile. And so let's go ahead and see if we can actually get the same values from exclude. Right? So here we go. So I'm going to go up here, and what I want is I want to get this value right here. And so I'm going to have equals, right? And then it's quartile exclusive, and then I want it to be of the full range of data, and I want it to be the third quartile, right? That third quartile right there. So I hit tab and enter, and you can see these two numbers match exactly, and that makes me super happy. And so I'm going to do the same thing down here, quartile, right, exclusive. I'm going to take the same data that I've been using, but now I'm going to use that first quartile, right, first quartile, and I'm going to hit enter, and you can see it's exactly the same number, and so that makes me super happy. If you want the hinge, right, that would be the inclusive, right, the data and the quartile, and again, it's not going to make much difference, right? So if I calculate the hinge here equals quartile inclusive of my data, right, and I do the third quartile, you can see it's a tiny bit different, but it's pretty close. It's within 50,000, right? And when you're talking about $1 million, that's not very much. And again, over here, if you do the quartile inclusive, you actually do the hinge of the data, right? And you use the first quartile because you want it to match. There it is, right? Oh, and so you can see very close. Again, right, it looks like it's about 60 grand off or something like that. And so again, 60,000 out of a million is not a lot. It's not a lot of difference, okay? And so there we go. And now you've learned something really cool. And so there you have it, right? Detailed explanations and Excel functions for measures of center and spread. And so we talked about when to use them. Mean and standard deviation are when you don't have any extreme values. And you can tell that when the mean and the median are fairly close together. If the mean and the median are fairly close together, that means no extreme value is pulling the mean one direction or the other, right? And so when there are extreme values, that mean is going to get pulled, use the median, okay? When you don't have extreme values and the mean and the median are close together, use the mean and the standard deviation, okay? Because that takes into account all of the values, and that's a better thing, okay? And hopefully this video helped, and if it did, that makes me happy. Until next time.